Hello and welcome back. My name is Corey and you're my rubber ducks for the evening. And this is the series of episodes where we are creating a custom programming language, a templating language, named Tang. And this is episode 80 something. I don't know, it was on the title card. I never remember what they are. And we have been working on this like I said, up in the 80s. We have a pretty good system, and this is an exploratory episode. In just about every other episode, I have had something that I'm working towards of saying we're going to build this feature, we're going to debug this, we're going to refactor this. And today I am needing to just kind of explore and see what I can do to help the efficiency of the code. And maybe nothing. Maybe I'll find something that I'll be like, okay, I need to research that, how to do that, because I am not an expert at this. I know enough to be dangerous, as I was going to say, most people would say about C++, that you know enough to be dangerous. But anyway, okay. So yeah, that's what we're going to do. So we're going to jump in, and in case you're wondering what I'm doing, for some reason my screw is loose in my watch band, and I was fixing it. Okay, let's see. I'm not on the right window, am I? No, I am not. What I normally say is I have nothing up my sleeves. Nothing is pre-prepared. And in fact, if we look at, there we go, Git log, you see the last commit was episode 86. Oh, so I didn't make a commit on episode for 87. That is, if we say git branch, you'll see that I have one where I tried to implement tail call stuff and it was slower. But we're going to revisit that. I might be able to make a change to that to make it faster. The jury's still out on whether or not I want to do that. But okay, that's fine. And we may not need to do it at all, but we'll think about it. And the other thing is, if I say git status, you'll see that there are no changes right now. And what I want to do is, first of all, in our make file, for our optimization, anytime you're worried about efficiency and profiling the code, you never use the debug branch. So I'm going to, right here, this OG, that is now going to become O3. And that will, on the right hand side now, when I say make test, it will turn up the most aggressive optimizations, and then we're going to explore this. Do I have the answer is no. I just kind of stopped talking, I know. But what I was looking for or considering is, do I have the timing of running our Fibonacci program? And I'm not seeing that, so we are about to run that after this is done compiling. And of course, I'm doing a fresh compile, and it's compiling 60 some odd files, and with the highest or the most aggressive optimizations, which takes a little longer. So this is taking a little longer than normal, and that's all right. And so I will say this, we're going to try to use a program called kcachegrind, and you can get that by doing like sudo apt install kcachegrind, and it will ask for your password, which is of course all stars, all asterisks, and I already have it installed, but it's as simple as just running that command. And let's see, everything's passing. That's always a good thing. And now if I run build apps Tang and feed in Fibonacci.tang, which is in our main file. This isn't going to do anything. I need to say interpret it as a script, so -s. Okay, and we get the number of that. And if I run this with time, there we go. 0.814, 0.812, 0.831. All right. And I'm just going to grab that and put it in my brain dump area, which is, of course, Notepad with a bunch of files I've never saved. That's what happens. All right, so one of the things I've been wondering about, on the left-hand side, I'm going to open our source program execute. Yeah, one of the things I've been wondering about is we've got this huge, and by huge, I mean down here, switch thing where all the cases are now highlighted. It can jump to any of these locations. That's a lot. And I don't know how efficient that is. Does it matter that I have the break inside of the braces here? I don't know. So what we're going to do, we're just going to look at the assembly code and find out. This doesn't scare me if you weren't watching right now. It scares me because I'm like, I don't know this that well. I did assembly programming back when I was in high school in the late 90s. Yeah, I'm old. And it was self-taught, and it was graphics routines that I was writing. I wrote like line drawing functions and, from one point to another point, and then turned them into rectangle filling and did it all in assembly. And what was funny is because I was using Pascal, Turbo Pascal, Borland Turbo Pascal, because that's the only thing I had available to me. And that's the only compiler I had access to. And it would allow you to do inline assembly. So I would write my program in Pascal and switch to inline assembly and write my routines. And I remember being like in band. I played the trombone. And I remember sitting back there. My friend Ben also did that, and counting up the number of cycles and saying, well, if I do it this way, it's this number of cycles. If I do it this way, it's this number of cycles, and hand optimizing. And anyway, doing that while the band director was working with the trumpets or whatever. I don't know. Just, yeah. I have not touched assembly since then. So it's been 24, 25 years. Yeah, this is going to be bad because assembly is a lot more complicated than when I was doing my simple stuff. The program we can use is obj dump, object dump, and if you just hit enter, you see all of the options. The option I care about is -s, which will show the source. And if I say man obj dump, does it give you more? Because specifically, I'm looking for a -l. There it is, line numbers up at the very top. Was that showing up here? S? Yeah, the lowercase l is not showing up on this screen. So, but if we do obj dump -S-L, I wonder if I can just do SL. I don't know. And then tell it what I want to look at. So we're looking at the build objects program execute.o. And of course it goes by way too fast. But okay, here we can see, yeah, how it tells me where in the program it is and what line number. And if I had left off the L, it might say where, but it doesn't say. Are there any others? I don't know. This is there's a lot of stuff here. Okay, so we're going to run it with L, and I'm just going to pipe this into less, which will allow me to scroll through slowly. And one of the nice things is that I can go up here and let's see. Well, just look for the word switch. There we go. Well, might as well start here. Line 81. What happens? Did not mean to make that really big. Line 81. /:81 should search for. And if I hit N, it'll look for it again. So it's in, okay, so this is in standard template library map.h. I'm not worried about that. That's in bit, singleton, pool. And I'm at the end. So if I go back out to the top. But what I care about is that it's in two places. Testing these two. Jump if they are equal to C50. And if I look at C50 there, that is going into program execute 758, and if we look here, :758, that is, okay, so that must be 757. Yeah, that's a stack pushback. So did I look at that right is the question. Could be. Keep going. On the switch. Oh wait, that's not the only place. So :81, right? :81. There we go. So this is the first one, and that's the second one. First, second, first, second, first, second. What I'm curious about is, can I go... I want to know where PC0 is. So that's line 61. Right there. It's XORing it out, which just sets the value to 0 in EBX, so it's in EBX. And then turns the number of elements in a vector, blah, blah, blah. That's at 766. Or 766. Why does it go all the way down there? I'm not sure. That's all of the 61s, though. That's odd. That it's doing it right down here amongst all the 700s, and I'm not seeing a jump instruction out of it. There's the XOR, and then XORing out this, which is number of elements in a vector. So vector of Tang garbage collected size. Oh, that would be the stack size. Yeah, I don't get why it's doing it down here. I tell you, it's been a while. Okay, either way, I'm going back to colon 80. Is it not line 80? '81. All right, and then the switch, line 82. Here it is. To compare the 2E, that's going to be the number of addresses. The number of opcodes, excuse me, that's what I meant to say, the number of opcodes. And we're comparing that against this RSI RBX4. That's going to be loading the bytecode location. So still part of 82. Jump if it is above to 488D. Yeah. So that's getting the whatever's in this bytecode sub PC. And then jump if it's above that, because we're comparing it against no, that's loading the effective address. Sorry, we're comparing it against this. Okay, jump if it's above to 488D. And 488D is doing something with a string, move, call, program execute unordered map, string, charge, any, well, that's giving it a pair. Then mem copy, blah, blah, blah. Sorry, as I'm looking through here, a lot of string stuff. Yep, there it is. This is the default case. So if it was above the number, it goes to the default case. So it just jumps directly to the default case, and that's unrecognized opcode. Okay. So this is the unrecognized or the default case that will create the unrecognized opcode. What is after that? Then we move a value, load effective address, move, and that's signed, and I don't remember. I think it's moving like a 32-bit to a 64-bit or something like that. Add and no track jump. Okay, why do I care about finding this no track jump? This is using a jump table for all of these, because then I bet if we look through here, like, do we find stack check 1? Well, that's 723. 84. Yeah, that's this one here. Or what about execute program check? Go to the very first one. Sorry. And I'm just doing a look through. So this is, I mean, it's optimized, which I just wanted to know, is it using a jump table? And the fast answer is yes, it is. It's using a jump table. So see if there's anything else. Okay, there's nothing else I want to look at now. Now, at least at the moment. So at least I know it's using a jump table, and it seems to be, when I was looking at this, you know what? I might as well show you. Vim make file, and this optimization, we're going to put that back to G. Okay? Clean make test-j 8. run it a second time. I'm missing a dependency still. I haven't found it. So this is compiling it without all of the fancy work. And I didn't do this on screen. I mean, I didn't do the optimized version. I did the unoptimized version. So now if I look at the object dump, and by the way, can we time this? 0.84. Yeah, whereas the previous one, so it saved us a couple, what is that, hundredths of a second. Okay. But what I wanted to show you is object dump, and now if I look for line 81, what we find out is that this one's a little bit more readable because it's less optimized. It is loading the PC size into EBX, and let's see, it'll use that when it needs to check PCSO on line 81, wherever that is. There, when it's using, well, RBX, yeah. The BX register. Anyway, but as it was going through, in order to get the size of this bytecode size, it is doing a lot more operations. The other one only had one operation. But in this one, again, in fact, now that I know what I'm looking for, there's going to be the no track jump. Yeah. And then beneath that, if I scroll down, we will see vector program execute 84. That's this stack check. That's right there. And then if I scroll down, we'll find another. Yes, I thought we would. Where are these? Execute program check. That's what I want. There's an execute program check. Here's a stack check. These are, so that's 92. Oh, so that's the execute program check and then the stack check. So, yeah, they're all there. There's another execute program check from line 90. Oh wait, that's right there. Did I go the wrong way? Maybe. 98, which is probably going to be this one here, and so on and so forth. Anyway, okay, so the optimization does very, very small demonstration of that it does actually have some power to it, or some use case. All right, so one of the things that I did, I kind of want to move all of these breaks outside, okay? And if I think it looks better. I don't actually think it's going to affect anything, but it will make me feel better about the code. When we get down to function, we've got to be careful, and that's another one that I want to or the function call, I mean. All right, now I just need to search for the breaks. Library, library save, library copy, function. Okay, function is okay. Assign index, add, subtract, multiply, divide, modulo, negative, not, less than or equal, greater than, equal, not equal. Index, slice, get the iterator, iterator next, is iterator end, cast integer, cast float, cast boolean, cast string, and now we're into the function one. Yeah, return, print. Nope, need a break there. Now, I want to see if this will. I'm not expecting a time improvement. All right. Now, I want to clean up this call func one. We kind of did this with the other one. That is when we did the recursive, and it was just, there was no reason not to. Okay, so for all of these, they're breaks, and this right here, if I look at it, it is a an if. So if I then just wrap all of these in an else, then I no longer need to break right there. The same way on this one, it's an if. So if this is now an else, then I no longer need to break here. Likewise, that says 4. While, where's the other breaks? Okay. I think we're good here. So we've got a break here and an if. So what does this match up with? It is also an if. So we can make this an else if, and then we no longer have to break, because when we get to the end of that one, it's just an else, and so we'll just keep on falling through down to the break. Okay, I think we're fine there. This is an if. Else, we'll get rid of that, and that's an if. So I can make this an else if. This also has a break. Is this part of an if? The answer is yes. So that means this becomes an else if. And this break can go away. And that, since this has a break, that means, and this is an if, that means I can make an else out of that. I think that's it. I'm hitting save, recompiling, rerunning. Everything passes. That's good. It did. Whoops. Don't know if it's getting worse or not. So all that we've done is, for every break that we removed, we're adding one, with the exception of in the function. All right, everything here looks correct. So refactor to make break statements consistent. All right, that's fine. Let's do some actual profiling. And we can do that by running, let's see, valgrind and tell it to specifically use call grind. Build apps tang -s feed in fib.tang. Okay, this is going to take a little while. If we look, we're going to max out at core. And because what valgrind is doing is it is tracking every thing that we do, every time a function is called. And you may say, well, we're not doing that many. Oh yeah, we are. And it's as it's being executed. So it's not just saying for every function that's defined. It's saying every time a function is called. That means every time you ask for the size of a vector or whatever else. The goal is for it to show us what is taking up all the time. What's taking up all the work. I'm hoping this works. And anyway, as I said, it does take a little bit of time. Look at this. How many references there are? 1,000 million, 12 billion. 700. Oh, yeah. Yeah. That's a lot. And then to open it, so what does this do? This creates a file called callgrind.out. And then the process ID. So if I call kcachegrind and then give it that file, it opened on this other window. I love the fact that the WSL, by the way, when I installed this program, I guess I can close this. There. It had installed quite a bit because it had installed all of the KDE stuff and other graphics stuff. But the WSL allows now you to have Linux graphical stuff, which is kind of cool. Oh boy. So view. Okay, so it's getting a lot of annotations. Let's just start looking. I'm sorry if this is small. I don't know of a way of making this larger. The Kali map. But I don't see what this is supposed to... Oh, I bet if I double click in it. Okay. All right. So just looking around, it looks like 100% of our time, or 99.96 was spent in the Tang program. Okay. And of that, so in our main, the majority of our time was spent there in the program execute, and look at this. Going from 99.96 to something. That means roughly, what is that? 60% of our time was in program execute. Well, that's our big switch statement. So going through there. And what's it doing all that time? Who knows? But if I look, let's see, because it's only called once, but this is called 63 million times. What is it? Okay. And the destructor for garbage collected is getting called 63 million. Yeah. 63 million times. That's a lot. We're running a Fibonacci. A naive Fibonacci. Okay, so I bet, if I had to guess, so we've got a 33, and what is this one? Okay, so I don't know what these are. Oh, but then it calls, it's almost just a wrapper around the destructor, which is taking up the majority of the time. Okay. So if I look at this one, this is our copy constructor. So we're calling this operator delete a lot. The mutex lock is getting called 29 million times. What is calling the mutex lock? Making an integer is getting called. Is that right? $9 million times versus a compiled function is being called 2 million times. So, it seems to me what I'm picking up from this, what is this? Garbage collected, operator, oh, less than. How many times are we calling less than? 2 million times. Garbage collector, vector of garbage collected in place back. That's probably the push back, is being called 14 million times. All right. So it would seem that if we want more efficient code or a more efficient runtime, then we need I know I'm just kind of talking here, but we need to reduce that. Now, is it possible? I don't know. How many times in order to compute the Fibonacci of, I think this is, are we only on 30, I think? catfib.tang. Yeah, we're only computing, but is that basically 2 to the power of 30? A little less than. Is that right? If it's 2 to the power of 30, that would be in the billions. Yeah, I mean, it's 1 billion, basically. 2 to the power of 30 is 1 billion, give or take. And if that is the case, and the fact that we're getting these in the millions kind of... Well, it's less than a billion, but... Is it 63 million? Maybe. So what do we need to improve the speed of? Maybe fewer copies of garbage collected. So what would that look like? Right now, we expect the function to be on the top of the stack. What if we could just refer to a function on the stack, just its stack position? So instead of instead of putting it onto the stack and then popping it off of the stack to call it, if we could just say, look at stack position X, Y, or Z. Maybe that won't work in every case, but that would get rid of a copy. Is that right? Yeah, because we wouldn't be peaking the value and then executing it. Yeah. We could probably do the same with the additions. But okay, so here's the problem. If we need to add 2 values, for example, if they're both 2 values that are on the stack, that's fine. We could have an operation to do that. But if we have I know it just kind of stopped talking. It's because I'm thinking. The problem is the way that the add works is sometimes you have an immediate value, sometimes you have a computed value, right? 1 plus 2 plus 3. It's going to need to compute the 1 plus 2 first? I don't remember. And that's a temporary value, but the 3, well, if it's not that would also be on the stack. Okay, but if it's a plus b plus c, a plus b would result in a temporary value and then c. Okay, so, It's going to take a little bit more work. I think it's doable. But, okay, so I think now, and the other thing is this mutex being locked and unlocked so many times. 50% of the time it's in garbage collected. 189 million calls to this. Maybe, is there a way to get rid of the mutex? The problem with the mutex is we've got a singleton object pool. Maybe that's the problem. Maybe we shouldn't use a singleton object pool. Maybe each context should have its own object pools. Maybe? I'll have to think about that. But that would get rid of the mutex stuff, which is taking up 5.13% of our time anyway. The operator new is being called 14 million times. But I think that's again because we're... Wait. It's being called 14 million times in the execute. The less than is calling it because it's needing to return the result of the computation, which is a Boolean. Which is probably being called by the less than, yeah. And then this one is here, which is the plus. I think that's a quick answer. How many times is plus being called? 1,346,268 times. Again. That's the only place the plus is called, so yeah. Add. But I wonder why the operator minus isn't. Oh, there's a subtract. Operator minus. And it is being called twice as often. Add those together and you get 3,900,000, nope, up over 4 million now. 4 million calls. Okay. So if we could make creating the garbage collected things faster and reduce the number that need to be created, and reducing them would be, pull this back up. See, when we say n-2, we're copying one here. Creating one, calling minus, which creates a new one, feeding that into fib, which is creating a new one. Same way here, creating one. So I think we need to, yeah, we've got to come up with, especially when calling the function, I think that would be the easiest. The first one is to add a new what's the word I'm trying to say? A new opcode to be able to, rather than pulling the top of the stack, to rather pull one from within the stack, just like a peak does. Yeah, that's what we've got to do. All right. So I have been staring at this for a little over an hour. We haven't done a lot. Well, I mean, a lot of coding. I did a very, very, very little cleanup. And is there anything else that I need to do? I should probably... the make file, that's fine. Tag, I don't think I need to update the documentation because nothing has changed there, just a little bit of, yeah. All right. Tag-A is episode.08. What episode number are we on? 088. Episode 88. Okay, and our message is... that is there. And we normally look at the number of lines. We're still sitting at 11,540. But yeah, like I said, we didn't do a huge amount of coding, but this is huge. Seeing that, first of all, a lot of time in the execute loop. The only bad thing is right now we can't see where in the execute loop that it's taking a lot of time. What portion of code. We can only see that the execute loop is taking up 99.96% of the time, which, I mean, quite frankly, it's that makes sense because it's executing the program. And what's not in the execute loop? I mean, excuse me, quite frankly, the execute loop is, you know, if we got the... No, that... I know. I just stopped talking. I was going to say, if we got the tail call optimization working, we could, I think, use that, because then each opcode would be its own function, and then we could see where all of the function time is being used, which opcodes are the most expensive. I don't. Maybe there's another way of doing that, but we'll worry about that later. But for now, I have my thing to be thinking about, and that is to create a function opcode that reads from the stack as opposed to reading from the top of the stack. And that will hopefully improve some of our time. And of course, then also in the back of my mind is getting rid of the mutex lock, because that is 29 million times is a lot. Yeah. Now, don't get me wrong, that's a lot of work, right? And we're only 7 times slower than Python. But yeah, there's surely we can improve that. And in fact, if we did get that working, I could see, and I know I should probably just turn this off, but I could see in our Fibonacci, as part of the creating, right now we already create values for the strings, right? The string literals. We could do the same thing with the 2, 2, and 1. That way they're only created once and referred to as needed. That could work as well. The bad part is that you would, if you were getting down to the n is less than 2, you would be creating a 2 and a 1, even though you don't need the 1. The payoff, of course, comes when you return n minus 2, n minus 1, and you only need to create that 2 once. I'll think about it. Anyway, okay. Having said all of that, we've come to a good stopping point. Again, not a lot done, but just experimenting and exploring. And that was huge. And also some interesting insight. So if someone has a better idea about how we can narrow this down, I would love to know how we can figure out what is taking up all the time. Because, yeah, we're losing a lot. So, all right. That being said, I'll turn everything off. Thank you again. Have a great day, and bye.